All right, good evening, class. So I wanted to work through an example of the problem-solving approach, and to motivate us tonight, I thought that we should start with a cinematic classic Super Soaker ad from the 90s. So stick with me for a second while we get our motivation established for this problem.
Did I forget to invite you to the pool party? Well, maybe next year.
On those occasions when you need to make a big splash, there's the Super Soaker 100. It has a powerful air pressure system,
Oh, Buffy!
a range of up to 60 feet, and a drenching spray. The Super Soaker 100.
It's a water gun of a higher caliber.
Also the 50, or the ultimate.
All right, so with our motivation clearly established, uh, the question I want us to approach tonight is actually, is this a safe child's toy? Um, we are proposing here to use a high pressure air system that will shoot water up to 60 feet across a room, potentially soaking Buffy and the other guests at her pool party. And so I want to walk through the steps of problem solving here with you tonight. So first, of course, the problem I asked you is this actually safe? But perhaps cast in a slightly more formal way, uh, what are we talking about in terms of air pressure? I don't know that I've ever seen a squirt gun actually deliver water 60 feet away. How pressurized is this thing? And is that something I want my child or even myself running around with? So, what pressure, capital P, in the squirt gun will get us 60 feet of horizontal range in our water? So, starting to sketch the problem and accumulate data, where we begin is with very little information. We know we've got a pressurized tank of water, and we know that we want to squirt Buffy 60 feet away. And our objective here is going to be to find what pressure does it take in a squirt gun to actually make this happen. So we've started to define the problem and accumulate the very scant amount of data that we've got here. Now, our next step is to get the theory established and the right equations and start simplifying that equation set. So we don't know much. We know we want to find pressure. We know we're starting with a length. And so how are these related? Now, this isn't a fluid mechanics class, but you might be able to intuit your way through this one. Um, the pressure in that squirt gun, the more pressurized it is, the higher velocity water will come out of the squirt gun. So that pressure, a form of potential energy, gets converted into velocity of water, a kinetic energy, and the velocity that that water is moving will control how far it goes. So the faster the water leaves the squirt gun, the farther away it can soak a guest at a birthday party. To formalize this a little bit, we're going to draw on physics, which many of you will have had, and we're going to draw on fluid mechanics, which I don't expect you will have had, so those equations will come out of the blue. First here, particle motion. So if we think about this as an idealized particle, and perhaps you took a physics class where you did a problem that was something like, if you aim a cannon at a certain angle, how far away will the cannonball hit the ground? That's where this equation comes from. It's horizontal length L, described as a function of a few different inputs. One, the angle at which you orient the velocity. And so for maximizing your distance, you would aim your squirt gun at a 45-degree angle up from the ground. So that's what we'll assume here. G on the bottom is the gravitational constant, and that L is the horizontal length that we expect our water would actually travel. For the first part of this, we're going to rely on fundamental fluid mechanics, in this case, the Bernoulli equation. And so I've written it here in orange. I don't expect that you all have necessarily seen this before or that you know where this came from. But in a typical design problem, we're going to pull on equations that are derived from fundamental physics. And so trust me that this is a good equation here, and as we move through the semester, we will make a point of showing you all where this comes from and not just pulling things out of thin air. But for our purposes today, trust me that this is our equation. And we're going to start documenting our assumptions here as well. So we're going to assume that this Bernoulli equation works. And by doing that, there's a whole bunch of assumptions that were already embedded in just getting us to this point. We're going to assume the elevations are not changing. So the tank of the squirt gun and the nozzle of the squirt gun are at about the same elevation. That the water inside the tank is not moving. So I'm putting the tank on the left-hand side and the flowing water on the right-hand side here. That there is no pressurization once the water leaves the squirt gun. It's just in the atmosphere under ambient pressure. And so what we can do is we can simplify our Bernoulli equation down to say, look, the pressure in the tank, that P1, divided by the specific weight of water, and that comes from the Bernoulli equation, the way it's formulated, and that's a constant we can look up. That's proportional or equal to, I guess in this case, the velocity of water squared divided by 2 times that gravitational constant. So here we're pulling together both a conceptual understanding, we're pulling together some mathematics to describe the problem, and we're documenting the simplifications and assumptions that we're making. The magical step 5, solve the darn thing. So what I've written here in orange is that Bernoulli equation just rearranged so it's solved for velocity. So you can see all I've done here is move the 2g to the other side of the equation. And we've got our same equation for particle. So written here in black, we've got our simplification of the problem. So we now have the ability to describe L, the length that water would be squirted, as a function of some constants, 2g, that specific weight gamma, a g again on the bottom that could cancel out, pressure in the tank P, and the sine of 2 times theta, which is the angle that we're aiming the squirt gun from the ground. So you could solve this. You can plug in L equals 60 and actually solve this equation out. What you get here is a linear relationship that the length that you can squirt water is directly proportional to pressure. So double the pressure, double the length that you can squirt, for example. When we solve this out for a length of 60 feet, we find that that should require a pressure of just about 1,900 pounds per square foot. Okay, so about 1,900 pounds per square foot is a mathematically correct solution, but it doesn't mean much to me. I don't have a lot of experience working in pounds per square foot. 1,900 pounds sounds like a lot to me. And so to help interpret or communicate the result of our calculation, I thought we will do a little bit of unit conversions. And so you can see here, I've multiplied this by 1 foot per 12 inches, and I've squared both of those, so I can cancel out square feet in the bottom with square feet in the top. And this turns out to be about 13 psi, or 13 pounds per square inch. That starts to be something that the average person can interpret. So for example, you may remember the Deflategate controversy over what pressure NFL footballs were at a few years ago. Those were at a minimum pressure of 12.5 psi. So the football that's being thrown around on the field is at about the same pressure that I would require inside of my squirt gun to make this work. Similarly, if we think about another child's toy, bicycle tires, there's a wide range out there, but bike tires are going to commonly range in, perhaps the teens would be an extremely low value. That'd be sort of a modern fat-tired mountain bike, and certainly a road bike could be easily upwards of 80 pounds per square inch. And so with these units that I understand and in this context, my ultimate conclusion here is, yeah, I think this is safe in terms of the pressure that we're putting in that tank. I don't think it's unreasonable that the same pressure we would have in, say, a football would be carried around as part of a squirt gun. So what we've done in this final step is help interpret and communicate these results in a way that someone who didn't do the calculation could understand. I hope this was at least an entertaining, if not interesting, example for you all, and it helps to talk through some of these steps of problem solving and see how you might set